Hey everybody, Corey and Victoria here. We are the Professors DuBois, and in this mini lecture, we're going to talk about hybridized orbitals based on the valence bond theory.
All right, so the valence bond theory is just one of the theories available, but it describes these shapes of molecules quite well. So we're going to go over that. And in this theory, it says that the atoms that get close enough, their outermost orbitals can overlap, and within these overlapped orbitals we can contain two electrons that form a bond. So the valence electrons from each of the atoms are either in a bond from these overlapped orbitals, or they're in their own orbital as a lone pair.
So let's take a look at one. This is a sigma bond from hydrogen. Remember the sigma bond is a single bond, and we're overlapping one s orbital. So remember, the s orbital has spherical shape, and hydrogen's single electron is in the 1s orbital. So when these two orbitals overlap, we can create a bond.
So it's not just between the s orbitals. So p orbitals can overlap as well. And in this case, we're showing you an example of a 1s orbital from a hydrogen overlapping with a p orbital from fluorine. And again, we just overlap. They share two electrons, and that forms a bond.
Yeah, remember those p orbitals have that dumbbell shape that's represented here.
That's one orbital. Those two pieces here is one p orbital.
One of three.
Right.
So we can have two p orbitals overlap. Here we've got fluorine bonding to fluorine, and the p orbitals are overlapping. You can see the overlap region forming that covalent bond.
And making a full octet for all of them. What this isn't explaining, though, is the shapes that we see of these molecules. So if you take a look at methane, methane is just a carbon with the 4 single bonds to hydrogen all the way around it, and it's a tetrahedral shape if we look at the Vesper model, right? So from Vesper, it tells us it's a tetrahedral shape, and these are 109.5 degrees apart. But if you look at the central atom, which is carbon, carbon has 2 electrons in an s orbital, and it has 2 electrons in p orbitals. And this would be that, okay, we have 2 electrons in our s, and we have 1 in this orbital, and say 1 in this orbital. And if you take a look at these orbitals, we have the spherical shape right around the nucleus for the s orbital, and then we have the p orbitals that are 90 degrees from each other. This does not explain how these overlapping orbitals could create this tetrahedral shape.
So this is where we have to bring in the idea of a hybrid orbital. So the way we can explain this is that these orbitals, the 2s and the 2p, are hybridized to form equal energy orbitals, 4 of them, and we're going to call these sp3. So we had the s orbital involved, and we have 3 p orbitals. So sp3 is the name of the hybrid orbital. So these hybrid orbitals each have 1 electron. Rather than having 2 in the 2s and 2 in the 2p, we have 1 electron in each of these hybridized orbitals, and now we have 4 bonding sites. Now, this hybrid orbital also has a different shape, and the shape is such that the bonding sites are going to be 109.5 degrees apart, as shown in this representation.
They get as far apart as possible because they're repelling. They're electrons. They're all negatives. Okay, so now we can see how we get that shape, that tetrahedral shape for CH4. If our carbon creates hybrid orbitals and they are in a tetrahedral shape, we have the hydrogen that just has the 1s orbital. It can come along and it can overlap with each of these 4 spaces, and we get our methane shape.
So let's look at ammonia. Ammonia has a lone pair of electrons, and so there's 4 domains, right? And we're going to use these domains to help us with the hybridization. So if I have 4 domains, I'm going to be sp3. That gives me 4 locations for electrons. Now, this one hybridized orbital is just holding the lone pair of electrons, but that's still a hybrid orbital.
And occupies a space, right? All right, so here's the methanol. I got excited and went right to methanol. So methanol has two central atoms, and you have to remember that geometries are around each central atom. So you have to look at each central atom separately to determine its shape and as well as its hybrid orbitals. So we look at the central atom and count domains. So for this carbon, we have 1, 2, 3, and 4. So we have 4 domains. That means we need 4 hybrid orbitals. That means we have 1 s and 3 p's all mixed together to make 4 sp3 orbitals. sp3 is the name of that type of orbital. So each of these central atoms will actually form an sp3 because this, if we look at this oxygen and count domains, it also has 1, 2, 3, 4. So each of these central atoms will create those hybrid orbitals, and then they can overlap in the middle and make a sigma bond, and they can overlap with the hydrogens to make sigma bonds with them. The oxygen has 2 lone pairs, and remember that your hybrid orbitals also contain lone pairs.
So let's look at BF3. This is the boron exception, we can call it. And if we count the domains, there's only 3 domains around this boron. So we've got, the orbital box electron configuration over here. It doesn't really show very nicely where we would have 3 locations to bond. But if we hybridize with 3 locations, this is just going to be an sp2. That'll give us 3 locations for bonds. So we're going to be sp2 hybridized, and there's going to be 1 vacant, empty p orbital that's not hybridized that's going to exist. So we've, again, the shape is also hybridized such that the distance or the bond angles are 120 degrees.
So the central atom will only mix or blend or hybridize enough orbitals that it needs. So if it has 3 domains, it's going to mix 3 of its orbitals, s, then p, then p. That's where we get the sp2. And in this picture, you can see how fluorine comes along with it has 1 p orbital that has 1 electron in it, so it can share and overlap and become BF3.
And those fluorines are not hybridized. They're just the p orbitals. You can see they have that dumbbell shape.
So here's sp. So beryllium is another exception, and it's happy with only 4 electrons around it as its octet, so it's an exception. And if it only needs 2 domains, so we have, beryllium can form 2 bonds, so it only needs 2 orbitals shared. So it takes one of its s's and one of its p's and blends them together and makes 2 sp hybridized. And it also has 2 unhybridized p orbitals just there with no electrons in them.
And here we're taking a look at how the fluorine can overlap with these hybrid orbitals and form a sigma bond or a single bond to the beryllium
in a linear shape. All right, central atoms in the 3rd period or below, remember, can expand their octet. That means they can have more than 8 electrons around them. And in order for them to do that, they need to hybridize some d orbitals as well. So s, p, p, p means 3, or we have 4 orbitals available in the s and p, but we're going to need our d's in order to expand. And pf5, we have 5 domains, so that means we need 5 hybrid orbitals. So s, 3 p's, and it needs 1 d to hybridize, and that's what it does.
So the lone pairs also need a hybrid orbital. We've said this before, but we're just showing it here with a different molecule. This one is the sulfur tetrafluoride, and if we draw the Lewis structure, we're going to see that we have 1 lone pair of electrons. So this has an electron pair geometry that's trigonal bipyramidal, where the molecular geometry of the shape of this molecule is what we call seesaw. And these are hybrid orbitals.
And here's our octahedral. So again, if we need 6 domains, we need 6 hybrid orbitals. So we have sp3d2. And that's a total of 6. And they arrange themselves in this octahedral shape. So this is the octahedral electron pair geometry as well as molecular shape.
So this is just a summary, and again, I just want to emphasize how we can count the domains, and they're calling it number of structural pairs on the central atom. We call this domains. If there's 2 domains, sp. 3 domains, sp2. That gives us 3 total. So we can use the domains to get the hybridization. Very simple with a little bit of practice.
And here's some practice for you. Determine the hybridization on each of the 4 central atoms. So I've marked the carbons as carbon 1, 2, and 3, and the nitrogen is also a central atom. So pause the video and give this a shot.
Okay, here are your answers. That first carbon has 3 domains. That's trigonal planar electron pair. And the molecular geometry is the same because there's no lone pairs. So 3 domains, sp2. Carbon 2 also has 3 domains. sp2. Carbon 3 has 4 domains, 3 hydrogens and a carbon. That's an sp3. And our nitrogen is an also sp3 with the 4 domains. But look at how the electron pair geometry is different than the molecular geometry because of that lone pair of electrons.
Thank you so much for watching. We hope you've enjoyed this and you have a better understanding of hybrid orbitals and how we use them. And come back again soon. Bye-bye.